Okay, let us welcome Dr. Porto.
Great. So I also want to thank the organizers for putting on a great conference. As a previous organizer of a previous ICAP, I have a special appreciation for what a fine job they've done, and it's an appreciation for how much work it is, and I really, really am grateful. Okay, so I'm going to talk about some simple experiments that we've done recently. And before I dive into what we've done and what it means, I want to give a little motivation. And pretty much any talk that you're going to see involving Rydberg starts with Rydberg atoms have strong long-range interactions. And that's the real driving force, because there's many applications for which you want controllable long-range interactions, ranging from many-body physics to quantum information processing, or even electric field sensing. There's a wide range of applications for Rydbergs that involve their long-range interactions. And they're particularly nice. They're particularly nice because they're very flexible. You have, by choosing which Rydberg levels you excite the atoms to, whether they're in the same internal state or different internal states, you can change the power law of the interaction, and depending on which n level you excite to, you can change the strength of the interaction over many orders of magnitude. And so they're really great tools for making two neutral atoms interact with each other at a distance. But they have one drawback, and that's they're highly excited states, and they're prone to uncontrolled decay, both blackbody and spontaneous emission. So typically, there's two approaches to using that interaction that avoids the decay, and one of them is to just work really fast. You do your experiment shorter than the lifetime of the excited state, and the higher the Rydberg state you use, the longer the lifetime is. It scales favorably with n. And so if you just do a really fast experiment, you can sort of access these interactions before something bad happens. And then another approach, which has been proposed in the last few years, is to work in the weakly dressed regime, where you don't have very much Rydberg population, and that decreases the amount of scattering that you get. And technically, there's a third proposal which we are interested in, or a third approach, which is to use the dissipation as part of the physics you're actually interested in. And if you have the scattering in the problem, you can study a dissipative interacting system, which can be interesting on its own right. So this approach says that you can do experiments on timescales longer than the lifetime, and I'll sort of introduce the idea behind this. It's basically the same thing as a light shift, but with interactions. If you put on a control laser field that's off-resonant from the Rydberg state, then you dress and mix in some of the Rydberg state, and the amount of Rydberg state can be controlled by how far you're detuned from the resonance, and that the resulting scattering is decreased by the decreased population you have in this Rydberg dress state. And the beauty of this idea is that even though you're mixing in a little bit of the Rydberg dress state, you still have access to the interactions between the particles. And what I'm showing here is the dressed Rydberg interaction between two particles as a function of distance between the two particles. And at a far distance, you see, this is for the van der Waals case, which is a 1 over r squared potential. At the far distance, you get a 1 over r squared potential, and as they get closer, the Rydberg blockade decreases the ability to have two Rydbergs in your two-atom excitation, and the blockade shuts off the interaction, and you get a plateau. So you're left with this soft core potential. And this is a very interesting potential, and it's one that you can engineer, and if you have enough laser power, the height of this potential scales with the Rabi frequency of your coupling and the detuning in this way. And if you have enough laser power and can detune, you can gain a lot in lifetime and have at least a little bit of interaction energy left over. This is a fantastic idea. There have been over 50 papers on dressed Rydberg or Rydberg dressing in the last 6 years since people started thinking about this idea. And in fact, there's been a couple of very nice experiments doing spin-dependent Rydberg dressing, some in Grant Biederman's group with 2 atoms, and then the Christian-Gross group with many atoms in a 2D array. So some further motivation for the experiments that we've done are we chose a very low end state, much lower than typical Rydberg studies that people are doing. And the reason why is because we were interested in the dissipative dynamics. The lifetime is short enough that we can get scattering on a time scale that we can see it and potentially use it. The blockade radius, the van der Waals blockade radius matches the typical lattice spacing. So if you're interested in some physics that's commensurate with the lattice that you're holding the atoms in, then you want the blockade radius not to be too big. And it scales very strongly with n, so you quickly get to very large blockade radiuses, much larger than a lattice site. And we wanted to work more in this regime. And it turns out there's a magic wavelength available near 1064 nanometers, and our dipole trap was naturally already there, so we wanted to be able to take advantage of that. So the system we have is atoms trapped in an optical lattice of order 1 atom per site. A lot of what I'll show you ends up being a little more than 2 atoms per site, but it turns out it doesn't really matter. We can drive the mod insulator transition to drive the double occupancy as pretty much to where we can't measure it, so we know we have 1 atom per site if we need. We use a 2-photon excitation, and the 2-photon Rabi frequency depends on the 2 laser beams, and we arrange it so that the blue laser beam is much more intense than the red laser beam. And to do these experiments, I want to emphasize that it's not just we were interested in lattice physics. It turned out the optical lattice was essential for the experiment. One, the Lamb-Dickey effect suppresses the recoil when you scatter the light. And absent the optical lattice, we would get a lot of recoil heating, and we couldn't hold on to the atoms and count them after the fact. But also, more important, which we were surprised about, if you were to try this on just a BEC, not in a lattice, the single red excitation off resonant gives rise to superradiant Rayleigh scattering, and you blow the BEC apart in an exponentially amplified way. This was first shown, I think, with a BEC by Wolfgang Ketterle, and this basically made it impossible for us to do it in a BEC, and that's another reason why the optical lattice is important. So a couple of tools we have to control the initial condition. The Rydberg excitation is resonant only with the MF equals -2 state of rubidium. I should say this is rubidium-87. And we're using a set of microwave pulses. We can shelve some fraction of the population into a dark, non-participating state, and we can change the initial density of the Rydbergs available to us, of the ground state atoms available to us, without changing the overall spatial shape. And we have a couple of probes. One is just watching the atoms that are optically pumped into different MF levels and counting them up. And so we just count them up and measure the fraction that have been pumped as a function of time so we can get rates. And then another one is we use the 5p 1/2 state as the intermediate level for the excitation. And we can count 5p 3/2 photons at 780 nanometers that come out. And those photons that come out, given by a couple of branching ratios, give you directly the 18S population, because the 780 photons can only be created having gone through the 18S. So those are our observables, optical pumping, and then the 780 nanometer photons that are scattered. So first thing you do, you get your cloud together and you start looking for resonance. And we found resonance and then went and sat on it and turned the light on. And this is showing the photons that come out, which converted into an 18S atom number in the cloud. And what you see is that pretty quickly you get light, population in the 18S, as you would expect. And it saturates to a level lower than you would expect, but there could be blockade and there could be broadening, and there was no surprise there. If you detune by 45 line widths, however, on the same order timescale, we saw that there was a significant 18S population. And if you even detune further to 90 line widths, There's a significant population that arises within a few microseconds, and if you had just calculated the single particle expectation for the lifetime, you'd have something that's a factor of almost 1,000 longer, 11 milliseconds. And the population that we see is larger than even the long-term steady state population by factors of 10 or 20. So to figure out what was going on, we did sort of old school spectroscopy, and we measured the transition width as a function of our two control parameters and the resonant optical pumping rate. And this is an example of the results. If you look at the measured width, it varies substantially from as narrow as of order 100 kilohertz. The natural line width is about 45 kilohertz for this Rydberg transition, to over 8 megahertz, and it's not even saturated yet. So we ran out of 2-photon Rabi frequency to be able to do this. And the general trend is the width is broader if you increase the density, either shown here or shown here, in this direction, or broader increasing the 2-photon Rabi frequency. The resonant optical pumping rate also was a bit surprising. It turned out to scale linearly with the Rabi frequency, not with the intensity, which is the Rabi frequency squared. And per atom, it was actually slower at higher density, which for very, very short times, one might expect collective excitation, which has been seen in these Rydberg blockaded systems. So as a further qualitative test, we adjusted the overall occupation of the lattice sites to have on average 1 per site, or on average 2 per site, mod insulator order in the lattice, or BEC order, so you had number fluctuations in the lattice site. We messed around a lot with the microscopic configuration, and the results that I've just described were pretty much unchanged to within the accuracy that we can compare the densities of the different situations. And we did the experiments in a particular lattice, which allows us to control in a checkerboard fashion the spin state of the atoms in the lattice. And so we shelved every other atom in the lattice site, and since we were originally interested in van der Waals interactions, we figured that the van der Waals interaction of two nearest neighbors in a lattice like this is of order 2 megahertz, but the 1/R6 scaling is so large it drops substantially, and it should be much lower in a lattice that's had every other lattice site shelved. And it turned out the results are also the same that if you density adjust for them. So the general observations that we found is it's symmetric in Lorentzian, which is not consistent with something that would be van der Waals, because van der Waals is asymmetric. The optical pumping rate scales inversely to the ground state initial density, which is contrast with the typical superatom scaling. The line width scales with the Rabi frequency, and the optical pumping rate looks like the regular expression that you would have for strong dephasing, where gamma is dephasing in the system. And the 8 megahertz energy scale that is probably even larger, we didn't saturate it to find how big that could be, is incompatible with the van der Waals, which, as I mentioned, was on the order of 2 megahertz. So one of the first things we thought about was superradiance. So we could go in and measure the lifetime of the 18S state after different excitation strengths. And what we found is that independent of the excitation strength, the lifetime is basically the same and consistent with the natural lifetime of the Rydberg state. And so that ruled out superradiance as a possibility for this broadening mechanism. So to be a little more quantitative, we can take the fact that we empirically observe this relationship between the resonant rate and the Rabi frequency, and we have measured that under all conditions the lifetime is the 18S lifetime, and we can calculate the 18S excited population. And if you plot all of the data versus the 18S population, you see you get pretty good collapse under all conditions, and it appears that the 18S population is controlling the broadening that's going on. So the amount of 18S is what gives you the broadening. So we ruled out the van der Waals as an option. The culprit, we argue, is spontaneous, where by spontaneous I'm including black bodies. Some people take strong offense at that, but I mean it's spontaneous in the lay term, meaning it happens on its own. Some black body transitions to nearby P states, and these nearby P states have tremendously larger interaction energies, and they tend to be symmetric because the dipole-dipole interaction shifts states both directions. And this kind of thing has been seen in intentionally microwave-produced Rydberg, nearby Rydberg states, and you can see that the optical transition is broadened by microwaves that have been intentionally used to transfer the states from S states to P states. So to try to figure out how this would be scaling and see if this argument makes sense, we argue that the NP population in steady state is going to be proportional to the 18S population. This is something that I argued within the group from the very beginning, is if you have 18S population, you're guaranteed in steady state P population by just the branching ratios. And you can work out what that is. And we know that the 18S population is going to be related to the ground state population by the rate that you're pumping in the lifetime. So if we assume that the line width is somehow proportional to the dipole-dipole energy, that means it's proportional to the NP density, the nearby P states. And then we use this empirically observed relationship, and that would tell you that the line width scales linearly with the Rabi frequency and is a square root of the density, and the on-resonant rate would scale as 1 over the square root of the density and linearly in the Rabi frequency. And if you plot the data, not only does the scaling look approximately right, I'm plotting the data versus those parameters that I showed on the previous slide, but the overall scale is pretty good. If you can see, the scale here and scale here are about the same. And I would say fortuitously good, because we had to make estimates of how many P states were involved, and we don't know the microscopic details of what's going on. But the energy scales are right, and the scaling is approximately right. Just for comparison, if you try to do the same scaling argument with the van der Waals scaling, both the overall scaling and the collapse and the energy scale are incompatible. So that's kind of depressing news. So one of the things that we want to do is make lemonade out of lemons and study the dissipative interacting system. And we've been talking to Alexei Gorshkov and Jeremy Young, his graduate student, about putting together a model for this. And we're still at the early stages, but a couple of interesting observations is that if you write down the Hamiltonian for the system and include the dissipation, and you want to try to solve it, usually the first thing you do is you do a mean field approximation. It may be inhomogeneous, namely every atom is allowed its own local density matrix, but you average over that atom's density matrix. And what you find out is that the mean field effective Hamiltonian depends on the average coherence of the other atoms that are around the atom that you're looking at. And if you create those coherences spontaneously or black body, it turns out that you can't build up any steady state phase coherence. And if you run the simulation in this Gutzwiller mean field way, these coherences die out and you get no broadening at all. So a mean field approach explicitly like this doesn't work. So correlations in time or space are needed, and I'm approaching out of time, so I'll rush through this. And these correlations are beginning to work, but there's indications that you need to go to even 3 particle correlations in the system to accurately describe our parameter regime. So what are the implications? The biggest implication is that instead of having a scattering rate that's given by the population, the Rydberg, you potentially have something that's about n times faster, where n is the number of atoms you have in the dipole blockade regime. And the problem is a single spontaneous NP Rydberg, which happens n times faster when you have n atoms there, facilitates an aggregate production of more of the 18S's, and the whole system runs away. And if you look at our time-dependent data, this is the calculated scattering time divided by n for each of these 2 detunings, and you see that indeed we begin to get population at this shortened time scale. There are a couple of approaches you might try. One is a stroboscopic approach. This is showing the excitation as a function of the pulse width, and you see it's narrower at early times, and the idea would be that maybe you could excite for a really short time and then wait and let the bad P states decay away, and then stroboscopically apply it again. It helps, but it helps in a scale factor. You can't go faster than the Fourier limit, or you'll off-resonantly excite anyway. So here's the take-home message I would say for the talk. The Dress-Rydberg experiments have less time than sort of estimated. It's not to say that going to higher n doesn't help, or doing stroboscopic doesn't help, but there's a factor of n, where n is the number of atoms in your blockade radius, that you have to account for these cascade effects. It affects both the S and P state dressing. I already said that. I point out that it can apply to quantum computing architectures as well, because if you have a steady state 18S, S population or Rydberg population, as you're exciting it, you're guaranteed a steady state P population, for example, if you have S and P, and that's going to cause problems. There's a theorists will say there's an easy solution, and that's just cool down the entire experiment and get rid of the black body radiation, and that's true. I mean, not the easy part, but that would solve the problem. The stroboscopic techniques can help, and I think that the correlated physics is worth study into itself. I want to thank Elizabeth Goldsmith and Thomas Bouillet, who are the 2 main leads on this. David Norris did a whole lot to develop the laser system that we use, and we have theory support from Jeremy Young and Alexei Gorshkov, and I have a fantastic collaboration with Steve Ralston. Thank you.
Thank you very much for the talk. Okay, so it's a wonderful talk. So is there a question or comment from audience? I have one question. Is your dissipation process really down to the ground state, or really the process which loses phase among the atoms in the lattice?
So I'm not sure I fully understand the question, but we don't have a distinct microscopic picture of what's going on, but the idea is that the spontaneous or blackbody-driven P states have a much larger dipole blockade radius than the van der Waals blockade radius, and somewhere semi-classically there's a shell of 18S, ground to 18S, that's made resonant by that, even though you're very, very far detuned. And so the combination of the blinking on and off of 17Ps disappearing and 18S's appearing and 18S's turning into 17Ps, plus this large dipole-dipole shift causes broadening and dephasing that gives rise to the line width.
So it broadens the line width, but does those Rydberg atoms decay actually goes down to ground state, or it stays somewhere in the P state?
The lifetime is unchanged. So the 18S lifetime is unchanged. So the 18S population ends up remaining approximately the same. I mean, yeah.
Okay, thank you. Question? Is there a question or comment from the audience? Yes, Jeff, over
I'm
there.
here.
How?
Okay. So I had a question about superradiance, but microwave superradiance from S to P. Is there something that is included in your model, or like superradiant decay from the S to the P state, from 18S to the neighboring P state?
You're talking about in the model that was trying to microscopically describe?
Right, or is it effectively what you observe, let's say?
Right. It was, you can put the wavelength of the S to P is gigantic, and it covers the entire, cloud. So you would really think if superradiance is going to happen, it's going to happen on that. Two things. One, the lifetime isn't changed, and if there were superradiance on that, at least some fraction of the lifetime I would expect to be changed. And two, if you put that into the model to try to prepare some coherence on the other terms so that you can get a mean field effect from that coherence, they also in the numerical calculations decay away. It's not sufficient to maintain coherences that would give rise to that effect.
Interesting, thank you.
Okay. If there's no more question from the audience, so probably let's thank the speaker again. And let's move on to the next speaker. Okay. Next talk will be the Dr. Giacomo Roati from